Good afternoon to you all. My name is Danica Bajic and I'm coming from the Military Technical Institute in Belgrade. Today I will talk about our research on structural integrity and also about the electrochemical properties of the functional coating based on graphene nanoplatelets incorporated in polyvinyl butyral. Group of authors included in this research come from the Institute of Technology, Metallurgy and Chemistry in Belgrade and from the Faculty of Mechanical Engineering Innovation Center. First for start to introduce the materials that were used in our composite coating. These selected materials are graphene, as I said, in the form of nanoplatelets due to its high conductivity, high surface area. These are the properties of graphene that are making it a good candidate for the application in electrochemical purposes. And the other component, polyvinyl butyral, is a very good and very adhesive resin material, which is compatible with various substrates, so it can be, let's say, applied or combined with various carrier materials in further applications. And also it is good for the manufacturing process of the composites because it doesn't react with various nanostructures such as graphene in our case. We had the objective to evaluate the thermomechanical resistance and properties of this new composite coating material and to estimate the electrochemical behavior of this material that we produced. Regarding the graphene that we selected for our research, here are given several of the important features of these materials, such as, in our case, the grade of the graphene that we used had a thickness of only 0.55 to 1.2 nanometers. These were mostly single layer nanoplatelets, and it had a high specific surface area, which is important for the electrochemical application. It has also good conductivity, and this is the reason why we chose it. Regarding the supercapacitors, these are the energy storage devices that can be used for example, portable electronics. They are used because they can produce a rapid growth of low power electronics. Here in the schematic presentation, you can see the principle of the function of the supercapacitors. The energy in these devices is stored by the accumulation of charges at the interface between the electrode material and the electrolyte, the solution of electrolyte around it. There is no charge transfer between the electrolyte and the electrode. There is no chemical reaction. And what is important to say about the supercapacitors is that they can operate in a wide range of temperatures from -40 to +100 Celsius degrees. And due to that all, they have very specific, high specific power. Regarding our experimental part of research, first step was production, that is manufacture of the composite samples. We have produced our functional coatings using solvent casting technology. First, we have incorporated the nanoplatelets of graphene using like a temporary helpful solvent, ethanol, to disperse the nanoplatelets using ultrasonic probe. Then we have added the polyvinyl butyral powder and mixed it vigorously to obtain the dispersion and the deagglomeration of the nanoplatelets of graphene, because the graphene has a high tendency to agglomerate, which can be a problem further for the use. After we have prepared the dispersion and dissolved the polyvinyl butyral powder in it, we have cast it in the Teflon molds and left it for the ethanol to evaporate. Like this, we have obtained thin films, like coating materials, for a reference, neat polyvinyl butyral without the graphene nanoplatelets, and the other one of interest, the sample with graphene. This solution and dispersion of polyvinyl butyral and graphene in ethanol was also used as a coating to be applied on carbon matte, like a carrier material. So we have also produced the carbon matte coated with this specific functional coating for the electrochemical testing. Regarding the characterization techniques, we have used for a start FTIR technique to investigate was there some interaction between the nanoplatelets of graphene with the polyvinyl butyral. Then differential scanning calorimetry to determine the thermal stability and thermal properties of these coatings. To determine temperature of glassification. And we have done mechanical testing, tensile tests, and hardness determination. Also, we have performed the electrochemical testing that was cyclic voltammetry. Regarding this cyclic voltammetry measurements, this is electrochemical technique that is used to study the electrochemical properties of a chemical species. For example, what is done there? We are changing potential linearly with time, starting from some initial value to some final value, and then we are changing it downwards to the starting point, and we are registering the current with time. Then we are expressing the dependence of current from the potential, and we are obtaining these diagrams on the right. The first upper diagram is a theoretical ideal model that doesn't exist in real conditions, but this is something that we are all aiming to. And the other one is more realistic for good supercapacitors, for example. This is the shape that we can obtain in our experiment. In our experiment, you may see the experimental setup on this image and the experimental conditions that were applied in our research. And here is the equation according which we have calculated the specific capacitance of the investigated material. And now we come to the results. First, to discuss FTIR spectrum. As we may observe the FTIR spectrum for neat polyvinyl butyral and polyvinyl butyral with incorporating graphene are very similar, but there are still some differences that are indicating that there exists some interaction between the incorporated graphene with the polyvinyl butyral matrix. Here we may observe somewhat more pronounced peak of hydroxyl groups. Then we can also observe CC bonds and PVB carbonyl stretch. This may be not very clear, but this is on the right side of the spectrum. Okay. Here we have presented the tensile test results. We have done tests on 4 specimens of each kind, and we have taken the mean value with standard deviations. What is important to note here, tensile strength is actually similar for the neat and nanographene modified polyvinyl butyral, but the elongation is pretty different. What can be observed that when we add graphene, the elongation at break and maximum elongation are different, and it is smaller for the graphene modified polyvinyl butyral because each particle, each nanoplatelet of the graphene represents actually a discontinuity in the material. So this is why it elongates less than the neat material. PVB is known as elastomeric thermoplast, so it really has good toughness, good tensile properties, but when it is modified with some particulate additions, it loses some of its mechanical properties. On the other hand, we have obtained increased modulus of elasticity, which means that this new material is more brittle. Okay. Then results of hardness of the coatings are shown from the both sides of coating. We have tested the hardness on the top side and the bottom side when we have taken out our composite samples from the Teflon molds because the results were different. So we wanted just to point out that in some point, after the ethanol evaporated during the solidification of our composite films, part of graphene like sedimented on the bottom. So we have a somewhat bigger hardness from the bottom side than from the top side of the composite coating samples. And of course, as expected, we have higher values for the composite samples containing nanographene platelets. Differential scanning calorimetry has revealed the effect of temperature on our composite coating samples. As expected, we have obtained increase in glass transition temperatures. We have done the test in 2 heatings because when testing polymer materials, it's common to do a first cycle of heating, then cooling under control conditions, and once again heating to to exclude some retaining stress or some polymer stress between the molecules. So as more relevant result, we are taking most often the temperature of glassification from the second heating cycle. As we may see here, our temperature of glassification has increased due to the presence of graphene nanoplatelets. And now to the electrochemical testing results. Cyclic voltammetry results comparing the untreated carbon mat covered with only polyvinyl butyral, and carbon fiber mat with polyvinyl butyral and graphene nanoplatelets. As we may see here, the basic, the black diagram on the left has the smallest inside surface, and the other two are having higher, that is greater surface between the lines of the graph. That means as we are calculating the capacitance as the integral of this surface, that means that our nano-modified coatings are having better electrochemical properties. And on the right side, we have also compared 2 different carbon mats covered with graphene in 2 different ways. What is the difference between carbon mat, the first one and the second? The second one was 2 times coated, like a double amount of our functional coating was placed on the sample. So this means that with our new graphene modified polyvinyl butyral coating, we are obtaining increased currents in comparison to the untreated carbon mat, which means enhanced capacitance. Also, it is important to observe the stability during many cycles of the test with this method. First, a diagram on the left is showing that we have performed 500 cycles of test, and in this diagram we have the results for the second cycle, the result after 300 and after 500 of cycles of the test. And it is interesting to note that there are practically the same results after 300 and 500 of the cycles. There is a difference between the second and the 300, but overall loss is not high. So it's only 5.5%. And then we have a stability from 300 to 500 cycles, only 0.60% loss in our case. And on the diagram on the right side, we have a diagram that is showing the actually stability with the increase of number of cycles. That is, the capacity is very stable in many cycles. Also, on other observed sample that contains graphene, we have similar results, but what is interesting to note, on the right side, we have increase of the capacity, which means that after more and more cycles, actually the electrolyte is penetrating between the some remaining agglomerates of the graphene nanoplatelets in the material. In electrochemistry, as I told in the beginning, it is important to have high porosity, high specific area of the material. And in our composites, although we have performed ultrasonic deagglomeration, although we had intensive mixing of the solution in the beginning when we prepared the material, some of the graphene nanoplatelets remained agglomerated, and during time, after many cycles, the electrolyte is actually penetrating between the agglomerates and getting approach to all the layers of the graphene. So this is why we have actually the increase of the current and the capacitance during time. That is during a number of bigger and bigger number of cycles. And to conclude, after all, in our new developed graphene-based polyvinyl butyral coating, FTIR technique has confirmed that these two components have interaction, and this is actually a consequence of chemical groups on the polyvinyl butyral that interact with graphene. Also, some of these chemical groups are remaining from the preparation procedure. Some of them are a consequence of the ethanol presence during the mixing and the agglomeration of the particles. Presence of the incorporated graphene particles has provided higher hardness of the new coating. Also, it has affected the mechanical properties in the regard of higher modulus of elasticity, but smaller maximum elongation. These new composite coatings have improved thermal stability, that is higher temperature of glacification, and this makes them a good candidate for electrochemical applications. So we are not making just some powder material that has good electrochemical properties, but we are making some material that can be applied in real products, in real supercapacitors, or maybe some electrodes or batteries. And that was actually the point. But in further research, we might actually include optimization of the production of our design of our composite material, maybe to improve the agglomeration of the graphene material, and also to investigate long-term stability and cycling performance of the material.